Okay, um, so we're going to be talking about relations today. And in particular, we're going to look at what it means to be a symmetric relation, what it means to be a reflexive relation, and what it means to be a transitive relation. But to begin, I just want to define what a relation is and talk about why we care about them. So given that sort of the mission of this class is to help understand mathematics from the ground up using logics, sets, and other tools to help us make sense of all the other tools that we typically take for granted when we're doing math. Today we're going to be taking a look at the sorts of relationships that we get between numbers. So for example, we have the less than or equal to relationship, the equal relationship, the greater than relationship, and a few others that we'll take a look at today. But something to note is that all of these things are actually telling us something true. So for example, I can say that 3 is less than 5, and that's going to be a true or a false statement. I could say that 17 is equal to 4. That statement is false, but it's still a statement. It's still something that we can assign truth value to. It wouldn't make any sense to assign truth value to something like 3 plus 5 or sine of pi. I mean, what would that even mean? How could that be true? How could that be false? It doesn't really make sense to say whether or not that is a true or false statement. What the relations that we're looking at today give us is some way of assigning a truth value to this relationship between two different numbers. Here we go. We're going to start by defining what a relation is. And we say that a relation on a set S is going to be some subset R contained in the cross product of S with itself. And in that case, what we're going to do is we're either going to write that two elements are in R, or that X is related by R to Y, in order to say that X and Y are related. So here I've got an example of a set S containing some numbers, and then R, which is a subset of the cross product of S with itself. So the cross product of S with itself would be all sets of ordered pairs. So for example, the pair, you might have the pair 1, 1, the pair 1, 2, the pair 1, 3. You also have the pair 2, 1, the pair 2, 2, pair 2, 3, and then you've got pair 3, 1, 3, 2, and 3, 3. And that's going to be the set S cross S itself. And you should be able to see here that R, as I've defined it here, is just some subset of this larger set of S cross S. Okay? So what you should be keeping in mind right now is that a relation is really just some sort of subset of this cross product. It's really nothing fancier than that, but it's also kind of a whole lot more than that. It gives us a way of comparing, well, maybe not comparing, but it gives us a way of relating two different objects within the set. And so, for example, if I take back that set here, we might rewrite some of the elements here as 1 is related to 2, and that's going to come from this element here. Okay, we might also write 2 is related to 3, which we get from here. And something to keep in mind is that order matters. Here we've got 3 related to 2, and that's something that's not the same thing as 2 related to 3, okay? They both happen to be true in this case, but it's not something that's always going to be true. For example, we've got 1 related to 2 in this set, but we don't have 2 related to 1. And so we might write 2 is not related to 1. Another way of depicting or understanding these relations is by the use of a graph. And so here I'm going to draw out all of the numbers in my set. We've got 1, 2, and 3. And anytime that I've got something that looks like x related to y, in my graph, that means I'm going to draw an arrow from x to y. So let's take a look at our relation r. And this first element here is telling us that 1 is related to 2. So that means I can draw an arrow from 1 to 2. And the direction of the arrow is going to tell us which way that relation is going. So here for the second element, I've got 2 related to 3. So that means I'm going to draw an arrow from 2 to 3. This third element here tells me 3 is related to 2. So I can draw an arrow from 3 to 2. And then this final one tells me that 3 is related to 3. And for that, I'm just going to draw an arrow from 3 and loop it back to itself. And this can help give you a visual understanding of how this relation is playing out. Okay, so that's what a relation is. That's a way of helping you understand what a relation looks like. Now we're going to move on to defining special types of relations. And so we've got 3 different definitions here that I want to look at. The first one is a reflexive relation. And we say that a relation is reflexive if for every element in the set that it's a relation on, we have that element is related to itself. So in other words, R is reflexive if whenever you take an element X in your set S, then the pair of X with itself is going to be in the relation set. So let's take a look at our example from before. Is R reflexive? It might be tempting to think it is because we've got 3, 3 here, but actually it's not, because in order to be reflexive, it needs to be reflexive for every element in our set S. So in order for R to be reflexive, we would also need to have the elements 1, 1, and 2, 2. And that would make R a reflexive relation now. I want to add at this point, after watching the video through, you could also check using the graph to see if R is a relation by seeing if every element has a loop in it. So what that would look like. So here we've got our graph. You can check to see if R is a relation, to see if every single element has a loop like 3 does. Okay? Here, 1 doesn't have a loop, and neither does 2. So in order to make R an equivalence relation, we would have to add in a loop at 1 and a loop at 2. Okay, now moving on to the second definition here, we've got symmetric. Okay, and we say that a relation is symmetric if for every 2 elements in our set, whenever X is related to Y, then we'll also be guaranteed to have Y related to X. And so let's check to see if R is reflexive in this case. Well, again, it might be tempting to think that it is because we've got 2, 3, and 3, 2. But again, this has to hold for every pair whenever X and Y are related. And so in order to make R reflexive, let's take a look here. Well, here we've got the elements 2, 3, and so we check, okay, 2, 3 is in R. Is 3, 2 also in R? And the answer in this case is, well, yes, it is. We just looked at that. But now let's look at this first element, 1, 2. 1, 2 is in R. Is 2, 1? And the answer to that is no, it's not. We can look and see just by checking the list. And we've got 1 related to 2, 2 related to 3, 3 related to 2, and 3 related to 3, but we don't have 2 related to 1. And so R would not be reflexive in this case. But in order to make it reflexive, all that we need to do is add in that element that we're missing. So we can just add in the symmetric version of 1, 2, which is going to be 2, 1. And then we can check that whenever x and y are related by x related to y, then we also have y related to x. And maybe something that you're wondering is, well, why don't we have to add 1, 3 in? Why don't we have to add 3, 1 in? And that comes from the definition, because we need to see if x and y are already related in one way, then we have to have them related in the other direction as well. Because we don't have 1 related to 3 already, we don't need 3 and 1 to be related in the opposite direction either. And similarly, because we don't already have 3 related to 1 in that direction, we don't need to have 1 related to 3 in order to make R symmetric. I might have been saying reflexive throughout the past few minutes, so I apologize if that's confusing. Let's look at symmetry in terms of a graph. So here we've got x and y related. And so here we've got two elements, x and y, in our set. And let's say that we've got x related to y. Well, in order for R to be symmetric, that means we also have to include an arrow from y to x. Now let's say that we've also got a third element here, maybe z. And let's say that z is hanging out over here by itself. Okay, and it's got a loop from itself to itself. Well, we don't need to include any extra arrows then in order to make this a symmetric relation. We've already got x and y related, and we don't have y or x related to z, and so we don't need to include any extra arrows from y to z or from z to y. Okay, those are just throwing in extra things that we don't need. Okay. So now we're going to go on to the final term here, which is transitive. And we say that a relation is transitive if for every 3 numbers now, whenever we've got x related to y and y related to z, then we also must have x related to z. So you can think about this sort of like a chain of relationships. So we've got x is related to y, and then we've also got y related to z. And so here in terms of our graph or our chart, if we have this arrow here and we have this arrow here, then in order for R to be transitive, we also have to have an arrow from x to z. And it has to be an arrow specifically from x to z, not just a path from x to z, because we've already got that path there. So let's try and figure out what elements we need to add to our set here in order to make R transitive. Well, in order to do so, we need to look at relations that consist of 3 elements. So we can see here that we've got 1 and 2 related, and that we've got 2 and 3 related. So that means we have 1 related to 2. We've got 2 related to 3. In order for R to be transitive, we would need to have 1 related to 3 as well. But we don't have anywhere in here that 1 is related to 3. And so, in order to make R transitive, we would have to add that in. And let's just make sure that we've exhausted all of the possibilities. We also have this thing here that says 3 is related to 2. And so we'd need to check, well, is 2 related to anything else? Well, we've got 2 related to... Well, we don't have 2 related to 1, but we do have 2 related to 3. And so in order for this to be truly transitive, we actually need to have 3 related to 3 as well. And it just so happens that we already have that here. To help see that, maybe I should color code this 3 here with red, this 3 here with blue. This 2 in the middle is staying green the whole time. It's the same 2 that we're talking about there. In order for this to be transitive, we need to have the red 3 related to the blue 3. They happen to be the same thing, but this is maybe psychologically easier to keep straight. And so that exhausts all of the possibilities here, and so that finishes what we need in order to make R transitive. Okay. So now we're going to put all of the pieces together and talk about something called an equivalence relation. An equivalence relation is a special type of relation. An equivalence relation is a special type of relation because it has this property that it's simultaneously reflexive, symmetric, and transitive. And so it has all 3 of the properties that we talked about. And you shouldn't be surprised that if I told you that the equal sign is an equivalence relation. After all, it has the word equal in it. And so it would be pretty bad terminology to call something equal if we don't have an equivalence relation. Can you think of any other equivalence relations off the top of your head? They're not as intuitive maybe to think about, but try and see if you can come up with a way of making this relation here R. See if you can find a way of making that relation an equivalence relation. You might have to go back through a few times, make sure that you've got all the elements that you need, but you should be able to do that. There's one equivalence relation that I want to talk about here, which is equivalence mod an integer. Okay. And I'm going to call it equivalence mod n, which we write as 3 equals sign. So we might say that x is equivalent to y mod n. And it's tempting to read this thing here as a parenthetical remark like, oh, it just happens to be mod n. Don't get confused by that. Even though there are parentheses here, those parentheses are just helping us create some space between the y and the mod n. It's an important thing to have there. It's not just some side comment. Okay. And what do we mean when we say that x and y are equivalent mod n? It simply means that n divides the difference between x and y. And another way of saying this is that there's some integer k, say, such that we can write x as y plus that integer multiple of n. And so you should be able to convince yourself that perhaps 5 and 14 are going to be equivalent under, let's say, mod 3. And how would you check that? Well, you could either check to see that, in this case, n is 3. You could either check that, does 3 divide 5 minus 14? Or you could also check whether there's some integer so that you can write 5 as y plus 3 times that integer. In this case, that integer would be a negative number. It would be negative 3. And you can check that by saying, well, yeah, okay, 5 equals 14. Here we've got 5, 14, plus 3 times negative 3. And you should be able to check that that is in fact true. And so here, negative 3 is going to be that value for k. So equivalence mod n is a special type of equivalence relation. It's one that gets used all over the place. But in order to call it an equivalence relation, we should really prove that it is an equivalence relation. And so I'm not going to do all of the steps in this proof. There are the steps written out in my notes that I've posted on the website. You can read through that proof. But the general schema of the proof is, well, you have to check that each of the three conditions for being an equivalence relation are met. And in particular, that means that you have to check that reflexivity is preserved. And you can pause and take a look at this part of the proof if you'd like. You can also, after you've checked reflexivity, you have to check for symmetry. And after you've checked for symmetry and reflexivity, then you check for transitivity. Here, I want you to pause the video. I've got you started on the proof for transitivity. I want you to see if you can finish this proof, okay? So pause the video, give it a little bit of thought, and I'm gonna scroll on here in just a second. Your job is to find some integer k3 so that you can write x as z plus n times k3. And these are the things that you are given here. These are the things that you're given up here. So take a second, pause, see if you can figure it out. Okay, so here it is, the whole proof written out completely. In particular, I'd like you to take a look at this second to last line and this last line, so you can see if you can reason about why each of these statements, each of those equal signs are true. And I'll give you a hint, that information is coming from this paragraph up here somewhere. And once you've taken some time to think about that, go ahead and give this problem a try. This is pulled from the textbook that I will leave a link to in the description of the video. But you've got the set W of all the words in the English language, and you're going to define a relation on that set by letting two words be related if they have a letter in common. So your task is to figure out which properties of being an equivalence relation are satisfied. So in particular, that means you're going to have to check, does it satisfy reflexivity? Does it satisfy symmetry? And finally, does it satisfy transitivity? And you should be able to give a well-reasoned explanation for each of these as to whether it's true or not. And I'll let you know, one of them is false. So it's either not going to be reflexive, not symmetric, or not transitive. Your task is to figure out which ones it does satisfy and which one it does not.